Hello everyone, this is Samah Ayman along with my colleague Isra Fahmi, and today we will be presenting MonoFi efficient indoor localization based on single radio source and minimal fingerprinting, supervised by Dr. Hamada Rez and Dr. Mustafa Yusuf. So, indoor localization has been vital to many of our day-to-day life use cases since we spend more than 87% of our time indoors. And several technologies have been suggested to enable indoor localization, such as cellular technology signal and the Wi-Fi based approaches. However, despite the advancements in the Wi-Fi based positioning approaches, they are still suffering from their dependency on multiple access points. So that's exactly the problem that we're tackling in this project. We are presenting MonoFi, a novel Wi-Fi based indoor localization system, which depends only on a single Wi-Fi access point in their received signal strengths. And we're glad to report that our system achieved results that surpasses the state-of-the-art results by at least 140%.
So moving on to our contribution, we developed a new system named MonoFi. The system is based on deep learning to generate accurate and real-time indoor localization. Our model utilizes recurrent neural network to learn indoor location of a user from the temporary change of the received signal strength of a single access point. In order to reduce the data collection overhead, our system generates synthetic measurements of received signal strength for non-surveyed points in the space.
So the architecture of the MonoFi system is composed of two phases as illustrated in Figure 1, the offline phase for training the deep learning model, and the online phase for tracking and estimating the user location. The offline phase starts with the fingerprint collector application installed on the user's phone. This application collects Wi-Fi information from the connected access points at few discrete reference points, uniformly covering the entire test bed. The RSS fingerprints are then forwarded to the path generator module, which applies a spatial data augmentation by interpolating several synthetic RSS measurements at new points. This tremendously results in reducing the data collection burden and improves the model generalization to unseen data. Then the module generates paths representing the user movement trajectories, which are then used to form the temporal sequences of RSS measurements. Then the location model constructor module uses these sequences to train the deep learning model to estimate the user location in the area of interest. In the online phase, the real-time tracking of the user is performed by obtaining the Wi-Fi information of the connected access points at unknown locations. Then the location estimator module augments the captured real-time data with the historical data, then feeds this data to the deep learning model trained in the offline phase to estimate the current user's location on the map.
We installed our system in two indoor test beds with different layouts. These test beds are located in two different spaces. Therefore, they have different sets of associated cell towers. The first one is a lab of 11 by 12 meters, and the second one is a campus floor of dimensions 37 meters by 17 meters. The floor contains offices, labs, meeting rooms, and corridors. All graphs demonstrated are based on the second test bed, since it subsumes more abstractions and resembles a real space. The first figure shows the relation between the number of access points and median error generated by the model, and from the graph we can conclude that reducing the number of access points to a single access point actually didn't compromise the accuracy of the system. The second experiment conducted between number of used LSTM layers and resulted median error. And from the results we observed that using two layers will result in the best accuracy with only 0.44 meter median error. The third experiment was conducted between step size used between fingerprints and the resulting error. Finally, we compared the performance of MonoFi against the three cutting-edge Wi-Fi based indoor localization systems, and the results showed that MonoFi outperforms the existing solutions with up to 200% success rates. This is the end of our poster presentation, so thank you for listening and we'll be happy answering your questions.